thankful for all of you to invite me here. So this is the title. It's Approximate Ramsey properties of matrices and finite dimensional norm spaces. Okay, so what is that? This is the question, and this is the kind of question we want to understand. We will have an answer. So let us define the matrices. So you start with F is going to be either R or C, or maybe finite field, or a finite field, and given two integers n and d. N is always going to be, d is going to be always smaller than n, but so m of n cross d of f, these are the matrices. This is the n cross d matrices over f. And of particular interest will be I of n d, so they look like that, right? D here and here. I of n d of f is going to be on the rank d n cross d matrices. So this means that the matrix is in here. This is a standard thing. So you take all the columns, and these are linearly independent. Okay. The dimension of the image of A. So I am going to explain you some results concerning mostly about this, but I also have results concerning that. And yes, and I forgot to say that this is a joint work with Dana Bartosova and Brice Mombo. So what I was saying is that the results will be Ramsey kind of result, or approximate Ramsey result concerning this, but we also have about that, but I am not going to discuss about that. It's a little more complicated. So what kind of results? This is what I was saying at the beginning. So this is the question. As always, you give me D and M, and you give me number of colors R. Does there exist an N such that whenever you have a coloring of this set, of the set of all random matrices of this kind into how many colors, there exists some matrix R, Ramsey one, in n cross m, such that when you take the restriction of C, of whom, well, you are allowed to take any matrix here, going from D to N, injective one, and then you compose with this R, and this you want to be monochromatic constant, right? Well, as I said, this is impossible, this is not true. And there are many reasons, very easy reasons. If you analyze for a while, you will find many counterexamples. But this is not the end. What we can say. And what I mean by that is the following: is some kind of Ramsey degree of this problem. In the case of the finite field, it is a Ramsey degree. In the case of the infinite fields, it is not a Ramsey degree, it's a continuous Ramsey degree. And what I mean by that, so I'm going to change this thing. does there exist something? So in the case of a finite field, then for the infinite one, you will see that this is impossible also, so you have to change a little. So so given D, does there exist some collection which has to be finite, or some integer? I am going to do it like that, so R or D. So that whenever you give me M, whenever you give me R, there exists some N, such that for every coloring, again the same coloring, then I can find this R such that I can factorize, and I can find some D from RD into R, so that I got the following.
Okay, these are already given. There are two D's.
Yes, so rho. Yes, you are right. And of course, there should be also, I didn't say, well, there should be some error here, yes? And there is an assignment also. So there is this RD, and there are assignments, canonical assignments, call it tau n from I n cross D. This depends also on D, but I will not put it in RD, so that I can make the following diagram commutative. So rho, this is commutative. So you see, I reduce the number of colors to this number here. This is what I want to say. Except if I say like there is an integer of finite state, I don't really see what is going on. I want to have here really something with some structure. It will be finite sometimes, in the case of the finite field, but I want to see here not an integer, but something with some structure. So what is the result? So this is true in the case of finite field. I'm going to write it down. I'm going to write it down, not an integer here, but something with very clear structure. Is it clear what I mean?
RD is larger than R.
No.
Sorry,
This is, I give you that, so this exists.
Yes, but what's its relation in general with R? I'm trying to see
There is
what
no relation. It will be typically small because this is 27. And no matter how many colors you are using, 217, I will reduce to this number of colors.
Okay, so this is the number of colors to which
Yes, except I don't want to explain it like that. I insist on that because I don't want to have here an integer. I want to have here something with a structure. It will be finite in the finite field because it's finite, but you don't see what's going on. And also because when I will explain you the real numbers or complex numbers, then this is completely another story. Okay? So as I said, that this is true, and I'm going to write it down. What is true for? So this is a consequence. So let me write it down in the right way, in a precise way. So what is true? Is the following. So this is finite field. And now, given a matrix, an injective matrix A from this over F, where the values of the indices are in F, then I can define the following object. So A has a reduced column echelon form. So something which is like that. Well, something here, here there is some 1, etc. And here on top there is 0. This is a standard algebra. This is nothing So given this A, I can write it down like this A reduced, and then some B of A. B of A is now invertible, so B of A is invertible. And now, given this A, I am going to assign B of A, not B of A, but some equivalence class of B of A. And this will be independent of which is this. Well, this is a unique. There is only one, but if it is not the reduced one, it will be exactly the same equivalent class. What is the equivalent class? What is the equivalence relation important for this invertible? Is the following. So you have B and C. You say that B is related with C if and only if some order is the same. What is this? What is this order here? So given matrix which is like that, these are the columns. I can define in S to the D the ordering, which is the lexicographical, out of this. So I mean, each of the elements of F of the D will have a unique decomposition. Yes? And now I simply say that X is less than Y with respect to this B, if and only if this sequence, of course I forgot to order Fi with some order where I start with the 0. Yes? So I said that if and only if this sequence is lexicographically below this order. Is it clear? Yes? So, well, this is the equivalence relation, so there are only finitely many orders on here. So this is a finite set, and this is the set. This is RD. Okay, what is this? A statement? No?
Your letters look alike, so
Okay, so
V and X look very much alike. No, on the next line.
this one?
Yeah. Okay.
Well, you take the
The
coordinates.
components of X.
You take the coordinates and you compare it lexicographically, and that's it. Yes? Okay. Now, well, now of course I have this B of A. Now I have, who is going to be this? So now this will be all these canonical orderings. And this mapping here is A goes to the equivalent class. So going to be this equivalent class. Yes?
Sorry, what is called?
Canonical orderings like these ones. Those ones.
Okay.
Or if you want, this GLD model with this relation. Okay? Okay. And this is true. This is a result. Let's put here. So it is not like they stated. So I will put 2. Graham, Lieb, and Rothschild. But they do not state in this form. You can find this way in the work of Estevo, and so K. Pestov, and Todorchevich. And this has some application that I will explain and after concerning topological dynamics of some limit of these vector fields, which I will explain. Okay. Now, okay, this is done. So far, so good. Now, what is the next? Well, the next is to go and change f by r for the complex numbers and see what's going on. What I need to have, and this is a unique, of course. I didn't say, or I will not say because I will forget, but this object here will be unique in the right context. This is, in this sense, for this example, it is unique in the sense of the cardinality. You cannot reduce it. In the continuous case, it will be in the sense of a topological space. Metric space, to be more precise. Okay. What's going on now if you want to say exactly the same thing now, but for matrices on values with values in real numbers or complex numbers? Doesn't matter. Well, this doesn't work. So you have to find this. The equivalent of that, right? This is an obstacle that you have to solve, and the very next one, this is infinite. So you are entering into the epsilon world. So this will not be exactly commutative, but it will be epsilon commutative. It will be an approximate. But more important, of course, who is this object now? Well, and now it comes. Well, it's going to be, yes. Before that, there is a consequence of that, which is an exercise, and also I will have the same consequence in the case of real or complex, is that, remember that the Grassmannian D over a vector field is the collection of all the D-dimensional subspaces of V. Yes. And now, and this is how they state the result, but it's a consequence of that, it's an easy consequence of that. Well, the same three guys there. Is that for every D, for every M, for every number of colors R, there is an N, so that whenever you color the Grassmannians, the D Grassmannians of F to the N into as many colors, there is some Ramsey thing here, excuse me, there is a Ramsey vector subspace in this case. So there is a subspace of dimension M, so that C restricted to the Grassmannians D-dimensional of this V, this is constant, okay? And why this is consequence of that? Because any V is an image of a matrix in a reduced column echelon form, and if you see what this means that you will always end up in the same order, which is the canonical order. This is what it means. Yes? So now what's going on? Now this is the part about finite field. Now what happened with this? Well, this is a little more complicated than that, and I'm going to talk about what it is. So, well, given a vector space, so I'm going to start with the standard things, but maybe you are not used. Given a vector space over arrows or the complex number, n is a norm if, well, n of E plus W is smaller or equal than the triangle inequality. And number 3, well, the collection of all the norms over F to the, so N D will be norms on F to the D. That's the guy now. But I said, there is an epsilon. So what do I mean by epsilon? Well, I have to put a distance on this and also on here. Yes, so that it makes sense to talk about epsilon. And what is this thing? It's a very natural thing. This is the next thing I'm going to discuss. How you make this metric space. How do you make it? Well, it's rather easy. There are several ways, but there are 2 or 3 of them which are the more convenient ones. Okay, the first thing maybe perhaps I start with this. How do you make this metric? Well, you can think that this every A here is an operator. So there is an operator, P of A, from F to M to F of N. So if I put here M and N, this is now, so what I mean by that, this is P of AI, UI is the column. Yes, it's A multiplied by UI, is what it means. UI is the unit basis that is 1 in I and is going to be 0 elsewhere. Yes, the canonical basis of F to the M or F to the N. Well, I can compute the norm of this operator. Which is what? Is the maximum. In this case, everything is finite dimensional. So that M, yes, yes. Yes?
M and N are norms?
Yes, yes, yes. N is a norm, is of this. Yes, so in this way, well, I can define a distance between A and B, like, or if you like this, doesn't matter, it's the same, right? Yes? Good. So I am not going to use 2 of them, but only 1. Maybe, so this will be induced by this one always. So what I mean by that. I'm going to take in this talk M equal to N equal to the supremum norm. Yes? I can take it also with 2, with Euclidean, but this is something else. So what do I mean? I'm going to put it explicitly. So given a vector x, norm of x is the maximum of all the coordinates. Well, less than whatever it has to be, n or m. So this is the distance I'm going to consider. The definition is the distance between A and B is going to be the norm of P of A minus B as an operator from infinity to infinity, yes? The maximum, blah, blah, blah. So this is a metric space. Let's do it like that. This is metric. Of course, unfortunately, it's not compact. While in the other case, everything was finite. So there will be a little obstacle, but we will overpass it. Okay, this is about that. What about this collection here? Well, there are many possibilities. I will put you 2 of them, and there is a relationship between them. So given 2 norms, M and N, in N to the D, the distance, which will be 1 because of something, okay? This is the log of the identity operator Mn as before, maximum with the inverse, which is of course identity, and M. This is a distance. This is a multiplicative one, and this is now a standard one. This is a metric. So you have D with this one. Unfortunately, I know that there are too many D's all the time. I am very sorry, but yeah. I should have used D. I should have used another. Well, the other one is the following. This is distance about operators, and now there is another one which is more metrical, which is the following. You are going to have you are going to start with some norm P, which will be fixed. And now, what is this? Well, okay. So let's see. You have FD with P, and you have now the unit balls of FD with this one and with this one. They are compact. What is that? All the vectors so that m of x is smaller or equal than 1. And the same for the other. Yes, this is a compact. So I can take, with respect to this one, I can take the Hausdorff distance in between these two compact sets. Yes? Okay. Yes? Well, there is a relation between these two, which I wrote it down. So, but to put the relationship between them, I need to introduce another little concept, an ordering for ND, for the norms. What is the order? It's a pointwise order. So you have M and N, and D. I write M less or equal than N, if and only if M of X is always smaller or equal than N of X. Yes, a very standard order. It's a pointwise order. So, and of course, remember that if A is a strictly positive, A times M also belongs to D, to ND. This is another norm. Okay, what is the relationship between these two distances? So there is a little proposition here, which I will write it down. I will not prove it. You have this condition: if M0 and M1 are not very far away of being P, well, A and P are arbitrary, then you have this distance one I just said is B distance Hausdorff P, I said in there. Where is that? And this BP. And A. So this has to be verified, but it's true. So if you consider for this kind of M's, ND with D1 and ND with NP, with DP, excuse me, these are by ellipsis equivalent, yes? With a given constant A and B that I know from the beginning. For these ones, so let me write it down correctly. For this interval, I take this interval of all the norms in here. This is by ellipsis equivalent to to this one with the P norm. Good. Now, well, yes. These are all the norms which are in between this and that.
In that sense. So it's
Yes,
not
it
a
is an
norm,
interval.
just- yeah.
It is an interval of the norms. Okay, now what I said is that this Ramsey degree is going to be ND. Well, but I need, in addition to that, I need to attach to a given matrix an element of NB. And how do you do these things? So you have a given matrix in here. So I'm going to define this. Where it has N and D. I'm not going to write it down with a given norm P. P is a norm on F to the N. So I'm going to define, so given A, what is tau of A? Well, it's very easy. You pull back norm P by A. So it's going to be by definition, so apply to X. This is what I take A of X, and then I compute the P norm. There should be some P here, right? This is a norm because A is injective. This is very easy to verify. And now this is the Ramsey degree. I'm going to write what it is. Is it clear? It is the Ramsey degree, of course, when P is a very particular one, not in general. So I take P to be a supremum norm. Okay? This is the result. For every D, for every M integers, what else? Ellipsis constant L, epsilon error, and what else do I need? I think this is it. No, and then this is not compact, so I need to have an interval, and A and B. All these are positive, and this is always like that. There exists some N, so that whenever you have ellipses from this into any metric space whose ellipsis constant is at most this L, there is a Ramsey matrix a very particular one. So it has the property, well, this is an isometry. R is going to be an isometry. You just think as the operator define sending the unit basis to the image from Fm with the sub norm into Fn with the sub norm. This is an isometric embedding. And this will have a reflect on what is going on with the tau p, which I will say at the end. And there is some mapping G from this interval, well, the infinite norm, into the metric space. Now this G is ellipsis is the ellipsis constant of F, a little more ellipsis for distances bigger than epsilon, and I will comment about that in a while, for distances bigger or equal than epsilon, such that the following diagram is commutative. Okay, so I I didn't say what is that, but it will come in a while. What is that? Well, these are the collection of all the injective matrices, whose image is in here. Okay, simply like that. Remember that this is not compact, so you must do these things. Is it clear, the statement? It's the same kind of a statement before, except that now there are these A and B, because you have to. This is a compact, and this is not compact. Now, when this space, given space, is L infinity ends, then you have this Whitney's extension result that will allow you to have this. Whitney extension result says that you have a mapping going to L infinity n, ellipsis in a set, so you have some metric space Y, and you have a subset, and you have a mapping from A into L infinity n, F, which is ellipsis. Then you can extend it to Y, and the ellipsis constant is the same. Yes, this is a very particular of this, and a little more than that, the complex, but then the complex is not the same. And in the Hilbert in general, but if this is a subset of Hilbert, so in general you cannot do that. That's why I have to put this condition. But if this space is of this kind, then you can get rid of that. And really it's more elegant. But in general, you cannot do it. And now, of course, this implies something about the colorings, because the colorings are controlled by these mappings. Colorings are controlled by this mapping. Given a coloring, I mean a discrete coloring, on a number I can define f of c, which is simply the distance to all the sets which are monochromatic with this color. So the pre-image of each of the colors. So f of c of A is distance to the pre-images of each of the colors. Yes, this is the mapping. This is ellipsis. One ellipsis is a very nice mapping. And I say this because then this result, of course, has a consequence on the discrete colorings. You don't lose anything because of that. You can color. This controls that. That's what I want to say. Okay. Now, what is the result about the Grassmann? Yes. And again, I will not enter into that, but put in exactly what you want to have. What is, you can prove that this set, this metric space, excuse me, with one of these, okay? This is unique. If you have any other metric space having this similar properties, they will be bi-ellipsis equivalent, because you can use that to define bijection between then sets of this set of this metric space and the other given one, and then you extend it. And it will be bi-ellipsis because there are this constant there, blah, 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 okay? So this is a unique in a very strong sense. Okay, so now I will go to the Grassmannians. What is the consequence about the Grassmannians? Well, similar thing, except that now it will come compact, not this thing, but and it shows up the Banach-Mazur compacta, which is not well understood, but it's well studied. So let me state the result, and then I will So for every D, M, L, epsilon, and now there is no A and B, there is some N such that whenever you have ellipses from the Grassmannians, the D-dimensional Grassmannian of F to the N into metric space, there is a subspace which is not any subspace, it's a rich one. So as a matter of fact, and this is important because otherwise the uniqueness is not true. You have to reach all the colors. This is what I mean. Yes, I don't want to go to the details. So there is a V which, together with the infinity norm, so V is a subspace of Fn. I can consider it with the subnorm, and now I take the induced norm on this, and now this is another space, norm space, and I want this. This will be isometric to L infinity of the dimension of V, which is M. Okay, this is informative because of something else. And there is some G from the Banach-Masur compactum of dimension D into this guy, so that the ellipsis, so that G is lib F and a little more than that, some constant that I didn't say, which is a little more than 1 plus epsilon. It depends only on D. Is with this constant ellipsis for distances bigger or equal than epsilon. Of course, if this is the real numbers or L infinity n, you will get rid of that, exactly like that. And the diagram is commutative now. And you have this. Excuse me, you have the Grassmannians, the D-dimensional Grassmannians of V, you have F. And now you have the Banach-Masur compactum, which I will introduce in a while. And you have this, and you have this that I didn't say also, but it will come in a while. So this is the equivalent result of what Graham Lieb and Rothschild got in the case of a finite field. Of course, now it's way more complicated. Now, I have to tell you what is that. I have to tell you what is that. Yes? First of all, what is BD? BD is the D-dimensional, well, not D-dimensional because it's not D-dimensional, the D Banach-Masur compactum. And what is that? So on N of D, you consider another pseudo distance. So given M, which has to do with one of the ones I was presenting before. So let's call it like a rho Bm. And what is that? Instead of considering only the identity of operator, I consider any invertible. So I take the infimum of what? Of any matrix which is invertible, and I compute the norm with respect to M and N, and then I do the inverse. I could put that in this case, because you run over all the possibilities, it is the same modulo 2 than this. Yes? And of course I have to, this is a multiplicative. I have to put log on that. This is a pseudo distance because rho Bm of Mn is equal to 0 if and only if, because there is compactness around, if and only if the spaces Fd with M is the same space, isometric, to Fd with N. So you mod out. What do? You take Md modulo Bm equal to 0, and this is the Banach-Masur compactum. This is Bd, okay, with the distance. Now is this pseudo. Now this is, well, you understand what you have to say. I'm not write it down. This is the Banach-Masur compactum. This is this object here. And this is a compactum. It is called Banach master compactum because, of course, it's compacta, not like ND. ND is not so good. What is this tau? Well, I just said, right? So you have an element, a d-dimensional subspace of f to the n, say, and I have this, well, remember that I fix at the beginning piece the subnorm all the time. I can do it with another, but I take this space. This is a d-dimensional space. So it is not over f to the d, but I can move it to f to the d. So I can imagine that this is on f to the d. I take its equivalence class. Yes, all the norms which are the same, that the isometric is the same to this one. Yes, this is not very correct in the sense that this v is not fd, but you pull it to f to the d, you put it there, and then you do that. Okay. So this is tau bn of v, and now we go back. So, and it says essentially that all the colorings depends only on the type of the subspace as a Banach space with a subnorm. Yes? Any coloring you can imagine. Any. So if you remember, what I said at the beginning about the case of the Graham-Leib-Rothschild result, I didn't want here only just an integer. I wanted a little more. This was a quotient of matrices, invertible matrices, and this is the same. It's exactly the same, except now the quotient is something else. Yes, yes.
Okay. Can you use this epsilon Ramsey degree to actually compute Bayer degree? Can you improve Bayer?
I don't think so. I don't think so, because in this theory there is no.
The result is the most discrete.
And there is the problem that you have to find somehow, which is impossible, f inside. So this finite field inside R or C, and this is impossible. So it's another story. So there is 10 minutes left. So I'm going to mention some more consequences about that. And maybe I will mention how you prove it, only how you prove it, with not too many details.
What's the reason that you restricted yourself to infinity?
You will see in a while. Because there is a consequence which is true for infinity, which is true for 2, which is true for some of the other p's, but in general for other things is not. And this is the next thing, the last thing, which is a consequence of that, but when you want to prove this, you are using this other result. What you are really proving is this consequence. Okay? It is a matter of presentation. I think that like that is more general and maybe more clear. So what is these consequences? Well, there is this theorem, which is the approximate. Now I don't know if I write it correctly. Ramsey property of finite dimensional norm spaces. And it says what is written in there, which is the following. For every f and g, this is finite dimensional norm spaces. For every ellipsis constant L bounded, for every error epsilon, there is some Banach space H, which of course contains G, because otherwise the result is a triviality, so that G embeds isometrically in, so if you want in this way, this is non-empty. And 2, given any ellipsis mapping from the sets of embeddings, isometric embeddings between the smallest and the H. So these are T's from F to H, T linear, and T isometry means norm in H of T of X is exactly the same as the norm in F of X. Yes, this is an isometry. So anytime you have this ellipsis mapping on the any metric space, ellipsis constant at most L, what? There is a Ramsey embedding from G into H, so that the oscillation of F on R and any embedding between F and G, this is less than epsilon. Yes? Well, this is the key proof for the other thing. Is not exactly that, but a simplification of that, which is the really important and complicated part, which is the case where F and G are L infinity ends. So let me write it down. So this follows with some approximate, approximate theory. You have to use plus theory from for every D, for every M, for every L, for every, and if you want, I'm going to do it with an integers for every epsilon. There is some n, so that whenever you color all the embeddings from L infinity D into L infinity and into R many colors, I can find an embedding from the intermediate one. And I can find one of the colors such that if I do this, these compositions, I am always in the same color up to epsilon. Yes, and that's the key. Then there is some approximate. Is it clear what I said? For every D, for every M, for every R, for every epsilon, there is an N, so that you color isometric embeddings into R many colors. You can find an embedding from the intermediate to the biggest, and there is one of the colors, so that all these compositions have more or less the same color. This is what it says. Okay, that's the key. All this. How do you prove that? Well, the proof, I'm not going to do it, but is Graham, okay, dual Ramsey. Which is called Graham-Rothschild. Well, it is not exactly Graham-Rothschild, but they are equally, one can be deduced from the other. So by Graham and Rothschild, which says the following. So let me, well, you have to use it in a right way, right? There is some work that is not simply an application. Have to. And what is the Graham-Rothschild? Well, it is this is how often you explain it, but of course, then this does not mean that the Ramsey result, the standard one, and this one are equally difficult to prove. This is way more complicated. This has way more consequences, has Hale-Hewitt, it has many things. This is a really strong. And what it says, well, you can say in several ways. Consider ED of n to be the collections of all the partitions of n into D many pieces, exactly D many pieces. So it is about that. For every D, for every N, for every number of colors, there is an N, so that for every coloring of this set into R many colors, there is a partition, Ramsey partition of N into M many pieces, so that all the subpartitions that you can create out of this one are monochromatic. And you can imagine what it means to be a subpartition. You are allowed only to glue things, yes? You cannot split them. So that C restricted to this, let us put it like that. I'm not going to define it, but you can imagine this is constant. Okay? Now, two more things and I will finish. Well, I didn't really say too much, right? Because I said this, you use that, but the way you use it is the key. Well, this gives bounds of, for this n can be used to bound all these n's that shows up, for example, here, yes? But two more applications that I said in topological dynamics. Which was the origin of all this. So there is something called the Curari space. Which is like the Hilbert, I'm going to write it down in this way without being very precise. This is the Hilbert space for finite dimensional norm spaces. And if you like, because you are used maybe to this, is this continuous phrase